Hi, welcome to the first in a series of short instructional videos from Exego Nanotools, where we'll describe a range of instruments that we offer for particle characterization and analysis, how they work, and the applications where they can be utilized. The title of this first talk is Exploring Surfaces with the Acorn Area. Our agenda will cover why should we use nuclear magnetic resonance? What are the practical advantages of the technique? Why is it important to work with concentrated suspensions and the consequences of diluting suspensions? How does NMR work? The relaxation method and measurement techniques, the utility of the measurements, and finally, we will briefly describe the Acorn Area device itself and the various options that are available for the instrument. So why characterize suspensions using NMR relaxation? Most particulate materials are made or used as suspensions in liquids, and the majority of suspensions are concentrates. Further, it is the particle-liquid interface, no matter what the particle, no matter what the liquid, that controls product performance. And product performance is defined as what the suspension is designed to do or be used for. Nuclear magnetic resonance is uniquely sensitive to two very important features of any particle-liquid interface. The first is the extensive wetted surface in a given suspension. Here we can include size, shape, morphology, and indeed porosity. Second, NMR is also sensitive to the chemical nature of a particle surface. This would include the fundamental surface charge and thereby the type and number of functional groups, both of which will impact the wettability of a surface by a given liquid. This is encapsulated in a small schematic at the bottom right-hand side. NMR is unique in this because typically traditional characterization instruments are only sensitive to one of the features, for example, particle size or zeta potential, but not both simultaneously. What then are the practical advantages? First, any particle of any size or shape can be studied. It does not matter whether it is an active pharmaceutical ingredient. It does not matter if the particle is even a liquid. So you can work with emulsions and solid materials from alumina to zircon. Second, you can work with any liquid as long as it contains at least one hydrogen atom. So, for example, we can make measurements in hexane, but not carbon tetrachloride. Even mixtures of miscible liquids, such as ethanol toluene, can be used. This is a very useful benefit, particularly when working in non-aqueous media and when investigating the wettability of surfaces. Third, the solids concentration can be very high indeed. The limit is simply dictated by whether you can get the sample into an NMR tube. No dilution is necessary. Samples can be measured as they are prepared or used, and this is an industrially important benefit. The overall measurement time can be very fast. Of course, it depends upon the sample under investigation and the precision required, but it's typically less than 5 minutes. Only a small amount of sample is necessary, around 0.1 milliliter. And importantly, the technique is non-invasive and non-destructive. This means that samples can be stored in the NMR tube and then reanalyzed at any later date. NMR is indeed a very versatile technique.